Hello and welcome to part 2 of our lesson introducing the chain rule. There are many more videos posted in Blackboard and in this folder with examples that will be helpful and videos from other professors that are helpful. But this goes through our guided notes and this is part 2. So what we looked at before is basically when we have the power rule, what goes on with our function when we take a derivative. And I'm sorry for the in and out zooming. So what we see is if we have some function, and I don't know why this keeps zooming out like that, in like that. I'm trying to make this big enough for you to see. U to the n, y equals some inner function. There's two ways to look at it. You bring the n down in front just like you did before and reduce the power by 1 and keep the stuff inside the same and multiply by the derivative of what's inside. There's two ways of writing that. This is Newton's notation. This is Leibniz's. So if anytime I have something to a power as my function, the derivative is going to be n times whatever that inner function was to the n minus 1 times the derivative of the inner function. In the first step, you keep the inner function the same. That's going to be important for you to realize. So we're going to go down and try some examples. If you think you're getting it and you want to try these examples on your own first, stop the video and come back. I'll try to take space between each one of them so you can try each one individually. So here, problem 1. We have y equals 3x squared plus 5 to the 4th. The inside part of this, sorry, every time I go down to pick a new pen, it zooms back in, zooms back out, sorry. The inside part of this is this 3x squared plus 5. And the outside part of it is the last thing you do. You could almost think of this as order of operations. If I had a value of x, I would do 3x squared plus 5. And then I would raise that to the 4th. The and then is the outer function. So the outer function is something to the 4th. So y prime is going to be 4 times something to the 3rd. And that something's going to stay the same. The big mistake students make here is they put the derivative of 3x squared plus 5 inside. Don't do that. That goes in the outside. The derivative of 3x squared plus 5 is 6x. Hopefully that's like second nature by now, derivatives of polynomials. And then 4 times 6x becomes 24x times 3x squared plus 5 cubed. Do not multiply out the cube. That is not simplifying. This is indeed simplified. That should be what your homework takes as an answer. We're going to move on to problem 2. If you want to stop, write it down, try it on your own. You can do that. Okay, so if I had a value for x, I would square it, subtract 4, and then take its sign. So that tells me the last thing I would do is take the sign. So the first thing I want to do is take the derivative of sine. The derivative of sine is cosine. You should know that by now. And I keep the x squared minus 4 the same. This is where students really mess with that. Notice this stays the same. The inner function always shows up in the first part of the derivative exactly the same. But this I would be done if the derivative of the inside of the argument of the sine were 1, but it's not. The derivative of x squared minus 4 is 2x. So what I get, we write this out in a more standard method, is 2x times the cosine of x squared minus 4. So now x squared minus 4 is still the argument of the cosine. It was the argument of the sine. That's the way that will work all the time. I'm going to try to go down to the next problems here. You can stop the video again if you want to try problem 3 without me doing it first. Okay, the first thing I do when I see a square root is I write it as a power. That's been true for a little while now. 4x minus 6 to the 1/2 power. So I rewrite the problem into a form where I see, oh, this is a power function. I can use the power function rule. So my derivative is going to have 1/2 times what's inside to the negative 1/2, because 1/2 minus 1 is negative 1/2. I keep the inside the same. So then I have to look, the inside function was 4x minus 6. I have to multiply by the derivative of the inside function, which is a 4, and that will give me, when I multiply 1/2 times 4, I get 2 times 4x minus 6 to the negative 1/2, or 2. And I don't think it matters in your homework, which I didn't do that correctly. Hang on. 2 over 4x minus 6 to the positive 1/2, or the square root of 4x minus 6. You cannot reduce a 2 and a 4 because this is inside a square root. You can't just go doing that. You can't make this a 2 and this a 3 and that a 1. You can't do that, just as an algebra reminder. So this would either one of these forms would be a simplified answer. Problem 4. I could use a quotient rule here. I have division. That's not necessarily the easiest way to do this one. You stop the video now if you want to try this one. What I would do with this one is rewrite the problem to be -7 times 2t minus 3 to the -4. Now I have a power rule again. I don't need the quotient rule. You could do it with the quotient rule, and the derivative of the bottom would be 4 times 2t minus 3 cubed times 2 for the chain rule piece. This is a little easier, though, because now I'm going to multiply -7 times a -4 that I bring down from the exponent. I'm going to keep the 2t minus 3 the same. -4 minus 1 is -5. The inside function was this 2t minus 3. Its derivative is a 2. So the derivative of y with respect to t in this case is this. -7 times -4 is positive 28. Positive 28 times 2 is a positive 56. You get positive 56 times 2t minus 3 to the -5, or 56 over 2t minus 3 to the 5th. Hopefully that algebra is not mixing you up, because by now you should be good with negative exponents. And that is number 4. So in the summary, we can write out our derivative rules a little differently now. They're a little more complicated now that we're allowing for inner functions. Not everything's just the function of the single variable. It could be a function of the variable. And here are the general formulas. This would be very helpful to have in your notes when you're doing your homework and any other time you're allowed notes. So keep this in mind. Notice the derivative of cotangent is still negative cosecant squared of the same thing you were taking the cotangent of, but it's followed by the derivative of what you're taking the cotangent of. If you took the derivative of cotangent of x before, and I'm just going to, you had cotangent, you would have written y prime equals negative cosecant squared. And sometimes I put it in parentheses. You didn't have to put it in parentheses since it's a simple x, times, the derivative of what's inside, derivative of x with respect to x is a 1. We used to just skip the 1. Now what we're allowing for is if y is the cotangent of x squared, we get y prime is negative cosecant squared of the x squared times 2x, because that's the derivative of x squared. This just shows you that these du dx's are all what I call the chain rule kicker, the chain rule adjustment, so that your derivative reflects a change in the variable, not in a change of the inner function of the variable. All right, that's what I have for today. Thank you for watching, and email me with your homework questions.